the first session that is scheduled is on scientific hypothesis, laws and theories. This is the representation of various terms that is associated with scientific research. And at the bottom part you can see facts. We are observing many facts in nature, and it's actually a singular proposition. We can observe many facts related with something, or related with everything. We can observe many facts. And when you are trying to explain the fact, or if you are trying to generalize the fact, then we require some working hypothesis. Working hypothesis is required because we are attempting to generalize the fact so that we can finally make a theory how it is occurring. If you want to explain that, you require a working hypothesis. And basically the working hypothesis, ad hoc hypothesis and auxiliary hypothesis, etc., were supporting the actual hypothesis. And we will see the definition and explanation related with hypothesis and other related terms in the subsequent slides. So once we have a hypothesis, you can propose a model or a design model, and you can also derive rules and laws, and finally you can reach some theories. And these theories were actually very generalized propositions which can explain the facts. So throughout the lecture we will be handling these terms and how to I will try to define them. I will try to compare and differentiate between these theory, laws and hypothesis, etc. Then initially hypothesis is actually two terms, that is hypo and thesis. This hypothesis can be these two terms can be combined together to form the hypothesis. Now hypo means tentative or subject to verification. So it's not a confirmed one, it's a tentative or a something that is subject to verification. And thesis means statement about the solution of a problem. So a thesis is a statement about solution of a problem, but is it confirmed? No, because it's a tentative solution. It's a solution that is subject to verification. So it's not a confirmed solution. So a hypothesis is actually a tentative or a solution that is subject to verification to a problem. The word meanings, not word, is a word meaning of the term hypothesis is a tentative statement about the solution of the problem, and hypothesis offers a solution of the problem that is to be verified empirically or experimentally and based on some rationale. So it needs to be, hypothesis needs to be verified and confirmed. A hypothesis is an educated guess, you can also say that, based on an observation. So hypothesis generally it is derived based on one or many observations, and based on that observations we will reach an educated guess based on the observations and our findings. That hypothesis needs to be verified to confirm that one. It can be supported or refuted through experimentation or more observation. So the experimentation and further observation, or the experimental part of the research, is actually an effort for verifying this hypothesis, or it's an effort for supporting or refuting or rejecting the hypothesis. A hypothesis can be disproven but not proven to be true. So a hypothesis can be disproven or it can be rejected, but it necessarily demands that hypothesis to be proven true, because many hypotheses cannot be proven true without a proper experimental evidence, or sometimes there is no provision for performing such an experiment. So hypothesis never demands to be proven true, but hypothesis can be disproven or it can be rejected based on some of the experimental evidences. Example, if you see no difference in cleaning ability of various laundry detergents, you might hypothesize that the cleaning effectiveness is not affected by which detergents which you use. Maybe you select 10 different detergents and you can hypothesize that these 10 detergents were not actually not much different. They are all same. You can see that the hypothesis can be disproven if a stain is removed by one detergent and not by the other. So the hypothesis is proven is disproven or rejected only when one of the detergent is proven to be effective and one is not effective. So in that case, you can reject the generalized statement that all detergents were having the same efficiency based on their effectiveness. On the other hand, you cannot prove the hypothesis even if you never see the difference in the cleanliness of your clothes, and after trying thousands of detergents you cannot prove, because if all 1000 detergents that you are screening is giving you equal results, then also you can prove it, because the next detergent which is not available to you may be effective. So that possibility is there. So which means there is always a chance that the hypothesis can be disproven under another condition. Okay, so hypothesis cannot be proved because we are testing only limited conditions. And yes, okay, accept it. So what I am saying is that a hypothesis can be disproven because an experimental evidence will result in the against the hypothesis will result in rejection of the hypothesis. But since you cannot ensure all test conditions or all possible, so for example in this example, to prove the hypothesis you need to test all the possible detergents, then only you can say that it is a proven true, but naturally that is not possible. Okay, so that's the basic concepts about hypothesis. A hypothesis is an idea or a proposition that can be tested by observations or experiments about a natural world. So a hypothesis is an idea or a proposition which needs to be tested by observations and experiments, and it is actually occurring in the natural world. In order to be considered a scientific hypothesis, hypotheses are subject to scientific evaluation and must be falsifiable. So there are various hypotheses, scientific and other, and scientific hypotheses were actually they need to be supported by scientific evaluation. They should be subjected to scientific evaluation through experimental methodology, and there must be a provision to falsify it, which means that they are worded in such a way that they can be proven to be incorrect. So the hypothesis, when we are arranging the hypothesis or designing the hypothesis, the wording of the hypothesis should be in such a way that there should be a provision for scientific evaluation, and there should be a provision for testing it and rejecting or falsifying that hypothesis. Then only it is a scientific hypothesis. Okay. For example, you may say that God exists. I make a statement. But for scientific, there will not be any provision for scientifically proving that statement. So it is not a hypothesis, scientific hypothesis. Whatever conditions that I am adding, then also it is not within the confinement of the scientific testing parameters. So in that case, that hypothesis about the existence of a god or something that cannot be explained by our experimental parameters or confined to the experimental parameters, then we don't have any provisions to falsify that statement. So if there is no provision to falsify the statement or any provision to disprove the statement or reject the hypothesis, then that is not a scientific hypothesis. For example, when Gregor Mendel in 1965 studied the pattern of single trait inheritance of garden peas, he formed a hypothesis on the manner of how these traits were inherited. So the hypothesis designed by Mendel in 1865 where can be summarized something like this. In the organism, there is a pair of factors that control the appearance of a given characteristic. So that's a very clear statement. In the organism, there is a pair of, means that's two factors that control the appearance of a particular characteristic, flower color or height, etc. And the organism inherits these factors from its parents, one from each. So that's also a very clear statement that can be trusted. Each is transmitted from generation to generation as a discrete, unchanging unit. When the gametes are formed, the factors separate and they are distributed to each gamete, and later it is known as the law of segregation. And if the organism has two unlike factors for characteristic, one may express the total exclusion of the others, dominance, law of dominance. So this type of hypothesis that is designed by Mendel in 1865, actually they are statements that can be tested using some experimental methods. So that can be disproven. There's a provision for testing it and rejecting the hypothesis based on that observations. So this is how a scientific hypothesis is designed. There should be a clear statement, and it should be subject to scientific experimentation and falsification provisions. And another term that we want to familiarize is theory. A scientific theory summarizes a hypothesis or a group of hypotheses that have been supported with a repeated testing. So a scientific theory, it's a hypothesis or a group of hypotheses that are supported by repeated testing. So it's a more refined one. You know that in the previous slide we arranged that hypothesis in the lower cadre, and at the top position we have theory, which is tested and supported by various scientific observations and supporting hypothesis, etc. So the theory is actually a more accepted generalized term. So that's why we say that a theory is a more generalized proposition. A theory is valid as long as there is no evidence to dispute it. Therefore, theories can be disproven. Basically, if the evidence accumulates to support a hypothesis, then the hypothesis can become accepted as a good explanation of the phenomenon or fact. One definition of a theory is to say it is an accepted hypothesis, because there are sufficient evidence that is accumulated based on observations and experimentation, etc., and that supports the hypothesis, so that it becomes an accepted hypothesis. So then it becomes a theory. Example: it is known that on June 30, 1908, Tunguska in Siberia, where an explosion equivalent to the detonation about 15 million tons of TNT happened. Many hypothesize that has been proposed what caused this explosion, and it is theorized that the explosion was caused by a natural extraterrestrial phenomenon, and that was not caused by man. That was the hypothesis generated at that time. Is this a theory or fact? Actually, it's a fact, because that happened there. The explosion actually happened, so it's a fact. And is the event is a recorded fact. So, but one problem is that the theory is generally accepted to be true based on the evidence to date. Yes, till the date it is not disproven. Say some hypothesize that it is an extraterrestrial phenomenon that has occurred, but actually it is a fact. It is the event has happened, but the explanation and the evidences gathered till the date still didn't rejected that theory. So that means it still exists. The hypothesis still exists. And if there is a sufficient evidence that is gathered in recent years or even in the coming years against that, and with a proper explanation, scientific explanation on that one, then the theory will be, or this hypothesis will be rejected. And until then, it based on the available evidences, this stands to be true. This stands to be an accepted theory. So that's how the theory was. So Can this theory be shown to be false and discarded in future? Yes, certainly yes. And to scientists, a theory is a coherent explanation of a large number of facts and observations about the natural world. So the theory is usually that it should be internally consistent and compatible with the evidence, and firmly grounded on the base and based on this evidence, then tested against a wide range of phenomena, then demonstrably effective in the problem solving. So these are various features that is required for the theory. It should be consistent and compatible with the evidence or supporting the evidence, and also firmly grounded on the evidence, then tested against a wide range of phenomena, not only on a single very limited conditions or parameters, but it should have a broader scope, and also it should be demonstrably effective in solving the problem and explaining the things. Then only this theory is accepted as a satisfactory one. In popular use, a theory is often assumed to imply mere speculation, but in science, normally in literature or in some other cases, it's only a very theory is it may be a mere speculation. They don't require any evidence. But in science, something is not called a theory until it has been confirmed by many independent experiments and evidences. But normally there are other theories, not in science, but scientific theory, it should be tested by many independent experiments, and it should be supported with various evidences. Then only a scientific theory will become acceptable. Theories are more certain than hypotheses, and but less certain than laws. So it's laws were actually above the theories in the hierarchy. The procedures and processes for testing the theory are well defined within each scientific discipline. So based on the different disciplines that we are, and scientific disciplines that we are involved, the theories and their procedures and process for testing the hypothesis and the subsequent theories that will vary within different scientific disciplines. A law, the third one, it's a generalized body of observations. At the time it is made, this law is made, no exceptions have been found to a law. So for a theory, we can give some exceptions, but for a law, there is no exceptions when it is actually proposed. Scientific laws explain things, but they do not describe them. One way to tell a law and a theory apart is to ask if the description gives you a means to explain why. So if you can have the explanation, or you can ask the question why, and if that answer to the question why is given in that proposition, then it is a theory. But for a law, it may not give you the answer to the question why. For example, Newton's law of gravity. Newton could use the law to predict the behavior of the dropped object. It will fall down, but he couldn't explain why it has happened. So the law that always subject will fall down. Why it is happening, that may not be explained, or the reason for that fact or that observation may not be explained by the law. Always the objects will fall down. That's a natural law. But when you add the explanation, like why it is happening, then it is a theory. Example, okay, already I explained the case of the Newton's apple. As you can see, there is no proof or absolute truth in science. The closest we can observe is a fact, which are indisputable observations. So a scientist should not say the term proof, I proved something, or this is the truth. Scientifically, we cannot say that, never. But we can say that these are the facts, and these are the indisputable observations, and it is supported by evidence. We can say that. But you cannot prove 100% to 100% certainty that this is a truth. You cannot prove that because there are other parameters or other untested conditions and areas where you don't have any access, and in that case there is no absolute proof and truth in science. But based on our observations and available evidences, we can state the facts. That's what scientists will do. If you define proof as arriving at a logical conclusion based on the evidence, then there is proof in science. So usually some articles and some journals will say that, or some scientists, when they are writing the article, they will say that it disproved something. It's only a simple statement that based on the evidence, it's a logical conclusion. That is the only answer, and that doesn't mean that it is the absolute 100% unchangeable truth. Okay, so based on another evidence, or subsequently in the subsequent years, there may be other evidences gathered based on further research, and then they will say that okay, this is the truth. For example, previously you can say that the smallest particles, even before the discovery of the microscope, may be a larger object. Then with the microscope we have the say bacteria and other things. Then even now we can come to the level of atoms, and then atoms again split up into smaller subcomponents, and further there are even in physics you can see that the matter actually it is divided further and further and further, and it reaches very minute levels. And based on the available scientific technologies and tools available, they are dissecting the matter into finer and finer and finer components. And for example, 50 years back, this information was not there. For them, atom may be the smallest particle, or electrons, protons, and neutrons may be the smallest components. And the matter can be further and further divided, and that can be proved based on the available technology nowadays available. So similarly, the truth will vary, and the proof, what is proved at that time by the scientists will change because there are further evidences that is gathered in the recent years based on the new technologies and tools available. So that's why we say that the proof and absolute truth in science is not practical, but we can say that there are indisputable observations or evidences that support the facts. And if new evidences were generated, then we can also disprove the observations, and we can reach another logical conclusion. That's how science always works, and it evolves. And even if you define proof as arriving at a logical conclusion, so in science generally, as I mentioned, the term proof means only we reached a logical conclusion based on an evidence, and that doesn't mean that you proved it to absolute certainty. Okay. Then law. Again, it is if you are asked to define hypothesis, theory, and law, keep in mind the definitions of proof and these words can vary slightly depending upon the scientific discipline. For example, for science or biological science and physical science, or even nowadays psychology is also coming under science. Okay, so based on the disciplines, the nature of the hypothesis and theory and laws, and this is also practical even in humanities and social science also. Okay, so based on the discipline, their concept on or their definition on hypothesis, theory, and laws will be different, because a social scientist or a psychologist may not require your tools or your experiential pattern or that type of verification methods may not be required for supporting their hypothesis in their discipline. So what is important is to realize they don't all mean the same thing and cannot be used interchangeably. So from discipline to discipline, these terms will have different uses and different meanings. A scientific law is a description of a natural phenomenon or a principle that invariably holds true under specific conditions and will occur under certain circumstances. So a law is Actually, it's a natural phenomenon, but it holds true under specific set of conditions. It will not be true always, or it will not happen always, but that generally laws were stated under particular conditions or set of conditions, then only it will happen. Example, in the early 20th century, after repeated tests and rejections of all the competing theories, Mendel's laws of heredity were accepted by the general scientific community. So, repeated testing and different experimental evidences, these Mendel's theories were actually supported. These laws were supported by the scientific community. Now they have a law of segregation and also law of independent assortment. It's already explained, you know that. And lots of historical and scientific information about Gregor Mendel and his works were available in Mendel Museum. So all this type of scientific information, scientific experimentation at multiple locations by different scientists were supporting the laws, that is or the hypothesis of Mendel, which supports the law of segregation and law of independent assortment. Now there is a term called assumption. Assumption, postulate and hypothesis. You need to differentiate that three terms also. An assumption means taking things for granted, so that the situation is simplified for logical procedure. So usually when we write a formula in mathematics, we will assume something. Say x is constant, y is constant, so that then the formula will work. Or you can say that you can assume a theory is and assuming that all participants were boys, or assuming all participants were girls. So if you make such a statement, it excludes something, or it limits the scope of your arguments. So such type of assumptions, which means things to be are taken to be granted, that the situation is simplified for logical procedure. So usually when we are deriving formulas, we will assume, say x is constant, or x is assumed to be 0. So then the value of y will be this. So in a similar fashion, we can assume things so that something can be fixed, some parameters can be fixed, and assume that it doesn't have any effect on that. That experimental output. So such type of procedures were usually used for simplifying the complex formula or complex conditions. Assumptions are not the very ground of our activity as the postulates are. So when we come to the postulates, postulates is having a little bit more scope, but assumptions are actually limitations. They merely facilitates the process of an agreement, a partial simplification by introducing restrictive conditions. Restrictive conditions like x is assumed to be 0, then y is this. So such type of restrictive conditions were a part of the assumption. For example, the formula of statistics and the measurements are based on number of assumptions. Assumptions means restrictive conditions before the argument can become valid. Assumptions are made on the basis of logical insight, and their truthfulness can be observed on the basis of data and evidence. Then come to the postulates. Postulates are the working beliefs of most scientific activity. With many peoples, God and spirit is a postulate of a good life and a godly life. Postulates are not proven. They are simply accepted as at their face value, so that their basic work for the discovery of other facts can they can be used as a basic work for the discovery of other facts in nature. For example, you can say that praying will heal the disease, a statement. So to test that hypothesis, you need to accept that there is God. Then only the prayer, whether the prayer is useful for healing the disease, that can be tested only by accepting this postulate that there is a God, which you cannot prove. So that type of arguments where At the face value, you will accept that one. So this is the condition. Then you are going to test the further step. And that step can be tested. Like we accept the fact or accept as a fact that there is a God. And praying to God will heal the disease or will result in something. So that can be tested with some experimental conditions. And if you are accepting something at its face value, some arguments at its face value, then that can be a postulate which doesn't require to be proved or proven. Okay. Now, the next one is a hypothesis. It is a presumptive statement of a proposition which the investigator seeks to prove. So hypothesis already explained, we explained the hypothesis in detail. It's a condensed generalization, and the generalization requires knowledge and of the principles of the things or essential characteristics, and based on this hypothesis actually derived based on some knowledge, existing knowledge and observations and other things. So anyway, hypothesis already discussed in the previous slide. Now when we come to the nature of the hypothesis, it is actually conceptual in nature, which requires to be supported or disproven. And some kind of conceptual elements in the framework are involved in a hypothesis. It is a verbal statement in the declarative form. Usually hypotheses were a verbal statement in a declarative form that is subject to be to further testing. Okay. It is a verbal expression of ideas and concepts, and it is not merely idea, but in a verbal form the idea is ready enough for empirical or experimental verification. So as I mentioned earlier, the hypothesis is there should be a testing or empirical verification of there should be a provision for empirical verification for a hypothesis. It has an empirical referent, and it indicates the tentative relationship between two or more variables. It has a forward or future reference because that needs to be verified in future. A hypothesis is future oriented. So our statement needs to be proven, it should be supported or rejected based on the further observations and experimental verifications in future. It is the pivot of the scientific research or axle of the scientific research. All the research activities are designed for its verification. So if you propose a research activity, then certainly you should have a working or a hypothesis, and that hypothesis is actually, it should be designed for verification or empirical verification. Okay. The nature of the hypothesis can be well understood by differentiating it with other terms like assumption and postulates, etc. So already we explained that two terms. Then when we come to the functions of the hypothesis, the following are the threefold functions of the hypothesis. To delimit the field of investigation, because a hypothesis is actually used to delimit the field of investigation. You want to set an experimental condition and define that one. And to sensitize the researcher so that he could work selectively and have a very realistic approach to the problem, and also to offer simple means for collecting evidences to the verification. So if you have a hypothesis, then certainly there should be some provisions for a specific empirical or experimental verification based on the evidences. So these are some of the functions of the hypothesis. And there are four different kinds of hypothesis. And first one is usually it's in a question form. Question form. And a question form hypothesis is actually it can be, an example can be listed like that. Is there a significant interaction effect of a schedule of reinforcement and extroversion on learning outcomes? So some educational reinforcement and extroversion, that is to educational terms. So if there is any significant interaction between these two terms on learning outcomes, so that's a question or interrogative type, so question form of hypothesis. So you can test that one. So whether the factor A and factor B is having some interaction effect. So that's a specific question, and which can be tested and verified. So whether A is having an interaction on B or interaction with B, or A is influencing B. So that's a question format hypothesis. Then there is a declaration statement like hypothesis. There is a significant interaction with the schedule of reinforcement and extroversion, or A and B. You can take it as A and B in two conditions. There is a significant interaction between A and B on learning outcomes. So that means it's a declaration statement. We are stating it. That also can be verified and rejected if it is found invalid. Then there is a directional statement like extrovert learners better through intermittent schedule of reinforcement, whereas introvert learners through continuous schedule of reinforcement. So that's a directional statement. So we are setting some restrictive conditions on these experimental design, and extrovert learners will have a better learning outcome based on intermittent schedule of reinforcement or support, and introvert learns through continuous schedule of reinforcement. So these two statements, they are actually a directional statement which can be specifically tested on two directions. Then null form or non-directional hypothesis. There is no significant interaction effect on schedule of reinforcement and extroversion on learning outcome. So the assumption is a null hypothesis. Null hypothesis usually uses or is a statement like there is no significant interaction between A and B. So that is the primary assumption, unless it is proven otherwise. For example, you test the conditions, and if you see that there is a significant interaction between A and B, then the null hypothesis is rejected. Usually our research were basically focused on such null hypothesis until it is proven otherwise or rejected. Null hypothesis is rejected, then we can assume that there is no significant interaction between A and B, or there is no significant difference between test and control. So that's the form of a null hypothesis, which is a non-directional one. So these are different forms of hypothesis that can be tested. Is there any questions? Hello? Hello? എന്തെങ്കിലും ക്വസ്റ്റ്യൻസ് ഉണ്ടോ? Any doubts? Yes? Hello? Yes. എന്തെങ്കിലും ചോദിക്കുന്നുണ്ടോ? Pardon? Pardon? Which one? ചോദ്യം ഡയറക്ഷൻ. ഓക്കെ ഓക്കെ. You can see that ഇതിൽ ആദ്യത്തെ മൂന്നാമത്തെ കേസിൽ, അതായത് ഡയറക്ഷൻ സ്റ്റേറ്റ്മെന്റിൽ you can see that there's a specific direction. For example, extrovert learns better through intermittent schedule and intermittent of reinforcement. അതുകൂടാതെ എന്താണ്, ഇൻട്രോവേർട്ടുകളാണെന്നുണ്ടെങ്കിൽ അവർ കണ്ടിന്യൂസ് ഷെഡ്യൂൾ ഓഫ് റീഇൻഫോഴ്സ്മെന്റുകളാണെന്ന് നമ്മൾ സ്പെസിഫിക് ഡയറക്ഷൻ ആണ് അതിന് കൊടുത്തു കഴിഞ്ഞിട്ടുണ്ട്. അതായത് ഡയറക്ഷൻ ഓഫ് റിസർച്ച് ഈസ് ഓൾറെഡി ഡിഫൈൻഡ് ദർ, റൈറ്റ്? നമ്മൾ ഓൾറെഡി പറഞ്ഞു ഇത് ഇന്നതാണ്. മറ്റേ കേസുകൾ അങ്ങനെയൊന്നും പറയുന്നില്ല. അതായത് ആദ്യത്തെ എന്തായിരുന്നു, ക്വസ്റ്റ്യൻ ഫോമിൻ്റെ അകത്ത് നമ്മൾ ഇൻട്രാക്ഷൻ എഫക്റ്റ് ഉണ്ടോ എന്നുള്ള ചോദ്യമാണ്, അല്ലേ? സ്റ്റേറ്റ്മെന്റ് ഒന്നുമില്ല. അതേസമയത്ത് രണ്ടാമത്തിൻ്റെ അകത്ത് എന്താ പറയുന്നത്, ഡിക്ലറേഷൻ പറയുന്നു ഉണ്ട് എന്ന് പറയുന്നു, അല്ലേ? സിഗ്നിഫിക്കൻറ്റ് ഇൻട്രാക്ഷൻ ഉണ്ടെന്നാണ് പറയുന്നത്. പക്ഷെ ആ ഇൻട്രാക്ഷൻ എന്താണെന്ന് പറയുന്നുണ്ടോ? ഇല്ലല്ലോ. ഇൻട്രാക്ഷൻ പോസിറ്റീവ് ആണോ നെഗറ്റീവ് ആണോ ഉണ്ടെന്നോ ഇല്ലെന്നോ പറയുന്നില്ല. എന്നാൽ തേർഡ് വണ്ണിൽ എന്താണ് നമ്മൾ പറയുന്നു, ഇന്ന കണ്ടീഷനിലാണെങ്കിൽ ഒരെണ്ണം ഉണ്ട്, മറ്റൊരു കണ്ടീഷൻ ആണെങ്കിൽ മറ്റൊന്നാണ് ഔട്ട്കം എന്ന് നമ്മൾ വളരെ സ്പെസിഫിക് ആയിട്ടുള്ള ഡയറക്റ്റീവാണ് കൊടുക്കുന്നത്, അല്ലേ? എന്നാൽ നാലാമത്തെ കേസിൽ എന്തായിരിക്കും, നമ്മൾ പറയുന്നത് ഒരു വ്യത്യാസവും ഉണ്ടാവില്ല എന്നുള്ള അസംഷനിലാണ് വർക്ക് ചെയ്യുന്നത്. അതായത് ദർ ഈസ് നോ ഡിഫറൻസ് ബിറ്റ്വീൻ ടെസ്റ്റ് ആൻഡ് കൺട്രോൾ എന്നുള്ള ഒരു അസംഷനിലാണ് നൾ ഹൈപ്പോത്തസിസ് അല്ലെങ്കിൽ നോൺ ഡയറക്ഷണൽ വൺ വർക്ക് ചെയ്യുന്നത്. ആൻഡ് നമ്മളുടെ എക്സ്പെരിമെന്റേഷന്റെ ഭാഗമായി ഇഫ് ദർ ഈസ് എനി അതെ, നോർമലി എല്ലാം വരുന്നത് നൾ ഹൈപ്പോത്തസിസ്. നമുക്ക് അങ്ങനെ പ്രീവിയസ് ആയിട്ടൊരു അസംഷൻ ഇല്ല, നമ്മൾ ടെസ്റ്റ് ചെയ്ത് കണ്ടതിന് ശേഷം ബാക്കി ഉണ്ടാവുള്ളൂ. നമ്മൾ വിൽ ഡിസൈൻ എ കണ്ടീഷൻ in which you will incorporate a test and a control, and to verify the hypothesis you will see that whether sufficient experimental evidences were there to reject the hypothesis. So if the null hypothesis reject ചെയ്ത് കഴിഞ്ഞാൽ എന്തായി, then that means there is a significant interaction, അല്ലേ? If the null hypothesis is rejected based on experimental evidence, then that means there is a significant interaction between the experimental outcome. പക്ഷേ നമുക്ക് when we are designing such experiments, you cannot predict the exact outcome. എന്താണ് ഉണ്ടാവുക എന്ന് പറയാൻ പറ്റുമോ? ഇല്ലല്ലോ. അതായത് ഇന്നതാണ് അതിൻ്റെ ഔട്ട്കം എന്നത് മുൻകൂട്ടി തീരുമാനിച്ചുകൊണ്ട് നമുക്ക് ചെയ്യാൻ പറ്റില്ല. പല സയന്റിഫിക് എക്സ്പെരിമെന്റിലും അങ്ങനെയാണ്, അല്ലേ? നമ്മൾ 2-3 പാരാമീറ്റേഴ്സ് സെറ്റ് ചെയ്തതിന് ശേഷം അതിൻ്റെ റിസൾട്ട് കണ്ടതിന് ശേഷം നമുക്ക് പറയാൻ പറ്റുള്ളൂ എന്തായിരിക്കാം അതിൻ്റെ ഇൻട്രാക്ഷൻ, അല്ലെങ്കിൽ എന്തായിരിക്കും അതിൻ്റെ റിസൾട്ട്. അത് പിന്നീട് നമ്മൾ പരിശോധിച്ചതിന് ശേഷമാണ് ചെയ്യുക. അപ്പോൾ ബേസിക്കലി ആദ്യത്തെ അസംപ്ഷൻ എന്താണ്? ഇത് കാര്യമായ വ്യത്യാസമൊന്നും ഇല്ല എന്നാണ്. But based on the further experimental outcomes and observations, we will analyze the results and we will try to see the interactions, if any. അത് കണ്ടതിന് ശേഷം നമ്മൾ പറയും ഇത് ഇന്നതാണ്, ഇന്ന ഡയറക്ഷനിലാണ് ഇൻട്രാക്ഷൻ. അപ്പോൾ നേരത്തെ പറഞ്ഞ പോലെയാണെന്നുണ്ടെങ്കിൽ നമുക്ക് എന്താണ്, ഡയറക്ഷൻ സ്റ്റേറ്റ്മെന്റിൽ കൃത്യമായിട്ടൊരു ഡയറക്ഷൻ തരുന്നുണ്ട്. ഇതിനകത്ത് അത് പറ്റില്ല. ചിലപ്പോൾ അത് നേരെ തിരിച്ചായിരിക്കും. ചെയ്തു വരുമ്പോൾ എങ്ങനെയായിരിക്കും, നമ്മൾ സീലെടുത്ത പോലെ എക്സ്ട്രോവേർട്ടിന് എന്താ കണ്ടിന്യൂസ് റീഎൻഫോഴ്സ്മെന്റും മറ്റേത് ഇന്റർമീഡിയറ്റും ആയിട്ടാണ് നമുക്ക് റിസൾട്ട് വരുന്നതെന്ന് വിചാരിച്ചു. മനസ്സിലായില്ലേ? അപ്പോൾ അങ്ങനത്തെ ഔട്ട്കം വരാമല്ലോ. അപ്പോൾ അങ്ങനത്തെ ഔട്ട്കം വരുന്ന സമയത്ത് നാച്ചുറലി എന്താണ്, യു വിൽ റിജക്ട് ദ നൾ ഹൈപ്പോത്തസിസ്. നൾ ഹൈപ്പോത്തസിസിൽ അങ്ങനെ ഒരു അസംപ്ഷൻ നേരിട്ട് എടുത്തിട്ടില്ല. നൾ ഹൈപ്പോത്തസിസിൽ പറയുന്നത് ദർ ഇസ് നോ സിഗ്നിഫിക്കന്റ് ഇന്ററാക്ഷൻ ബിറ്റ്വീൻ ദ ഫാക്ടേഴ്സ്, അല്ലെങ്കിൽ അങ്ങനെ ദർ ഇസ് നോ ഡിഫറൻസ് ബിറ്റ്വീൻ ദ ടെസ്റ്റ് ആൻഡ് കൺട്രോൾ എന്നുള്ള അസംപ്ഷനിലാണ് നമ്മൾ വർക്ക് സ്റ്റാർട്ട് ചെയ്യുന്നത്. ബട്ട് ആഫ്റ്റർ ദ എക്സ്പെരിമെന്റൽ ഒബ്സർവേഷൻസ് we will see that the null hypothesis is other. If there is a significant interaction, we can reject the hypothesis, null hypothesis. Usually എല്ലാം null hypothesis ആയിരിക്കും നമ്മളുടെ ഹൈപ്പോത്തസിസ് പറയുന്നത്. നമുക്ക് അങ്ങനെ ഒരു മുൻധാരണ ഇല്ല, ഇന്നതേ ഞാൻ പ്രൂവ് ചെയ്യൂ എന്നില്ല, അല്ലേ? സാധാരണ മജോറിറ്റി എക്സ്പീരിയൻസിനകത്ത് നമുക്ക് അങ്ങനെ ഉണ്ടോ? അതായത് ഇത് ഇന്ന രീതിയിൽ തന്നെ ഇതുണ്ട് അല്ലെങ്കിൽ ഇന്നതാണ് എന്ന് ഇത് തന്നെയാണ് പ്രൂവ് ചെയ്യേണ്ടത് നമുക്കില്ലല്ലോ. അതിൻ്റെ ഇൻട്രാക്ഷൻ പോസിറ്റീവ് ആയാലും നെഗറ്റീവ് ആയാലും നമ്മൾ അക്സെപ്റ്റ് ചെയ്യും, അല്ലേ? That's why we are using null hypothesis. Okay. So when we come to the process of science, observation is the first one, because we are observing the facts. We have many facts in nature and we can observe them, and based on the observation of various facts, we will have some questions arise in our mind. So if it is so, why this happens? So you are trying to explain the facts, which is the process of induction. So arising various questions based on the observations. So that is the process of induction in the process. Then as a part of, once you got an induction, then you will try to derive some logic out of it to explain. If then statements will be incorporated. For example, if the condition is this and then if such a condition A and B exists, then the result should be this. That type of direction is possible. So usually a hypothesis is actually derived from that one. In the previous example, for example, if A and B or if C is kept constant, and then A and B will have a significant interaction, something like that. That type of logical deduction can be made from that observations, and which can support your induction, that question that you arised. Now see the example, or for example, okay, examples will be discussed later. And a hypothesis, usually a null hypothesis, an H0, where we say that there is no difference between observed and expected. So that is the concept of the null hypothesis. And H1, that is observed and expected are different. That is a other hypothesis. This null hypothesis is a H0, which says that there is no significant difference between the observed and expected. So such type of hypothesis can be derived. Then you have the experimental portion. you design an experiment to verify that hypothesis. You should get the results and observations, and based on the results you can reject or accept the hypothesis. Then sometimes there are alternative hypotheses were generated. Based on the results and observations, you can try to improve the hypothesis based on the additional observations that you got from your results. Then you can propose alternative hypothesis and again verify that. And remember, proof in science is not possible. You are only supporting the hypothesis or rejecting the hypothesis based on the available evidences. So this observation and induction, then hypothesis generation, experimentation, verification, and if the hypothesis is rejected, then you can propose another alternative hypothesis and go through this cycle. So this is how the process of research in science works. So you can see the flow chart in which there is you can define a research problem. So this research problem actually it is defined based on the available observations, and available observations may be in the form of various literatures available and facts available, and you can review the literature, review concepts and theories and previous research findings, etc. were analyzed, and based on which you have the induction and you formulate a hypothesis. Then you research you design the research experimental part and including sample design, etc. Then you collect data or execution of the experiments, then analyze the data and you test the hypothesis whether it is true or false. Again, you can if it is you can based on these assumptions or results, you can, if the hypothesis is rejected, you can redesign the experimental part or you can reformulate the hypothesis, and again we can go through this additional experimentation, and finally you can generate your research report based on the final output. So these type of processes were actually used for research process design. And this is another explanation where you will use observations or informations and the descriptions, that is a conceptualization part, and that observations and also scientific, philosophical and cultural background, personality of the scientist, these are all various influencing factors on this induction and generation of the logic or induction. So various observations, then philosophical thoughts and scientific facts, then even the personality of the scientist, etc. All these were affecting the intuition and logic or the induction process. So once there is a problem, you have the intuition or induction and you generate a hypothesis. And sometimes you will require auxiliary hypothesis. We will see in some of the other slides what is an auxiliary hypothesis. So anyway, hypothesis is generated based on these available informations and observations and other characters. Then once the hypothesis is there, you will deduce a logic to verify the hypothesis, and you will design an experimental part. Then deduce the state of affairs can be verified based on experimental output. Then there is a deduced state of affairs will be there, and after that, so this is the deduction process in which you assume that this will be the output. And observed state of affairs is obtained after the verification, experimental verification. You can verify and compare these two. So you are expecting a result and you are actually observing a result after the experimental part. So if these two are in agreement, then it's a confirmation of the hypothesis. Observed results and our expectations, where if they are matching, then our agreement is in confirmation with the hypothesis. Or if there is a disagreement with this deduced state of affairs or expected outcome and observed outcome, if there is a difference, then that means our hypothesis is in disagreement with that observations, so that hypothesis will be rejected. Okay, is it clear? Hello? Okay, okay. So in the process of science, the science behind the discovery that genetic material resides in chromosomes. So that is one of the discoveries in science. So we can apply this procedure, this process with uh, discovery of this genetic material in chromosomes. One example, specific example can be used. So we have observation, first step. Offsprings inherit traits from their parents. That is a very common observation previously existing. So from that observation, the second stage is a question. Where does this information responsible for traits reside? So that was a logical question that is generated. So again, there is an additional observation. The nucleus appears to be important. There is another observation. So based on different observations, such questions can be generated. So what is responsible for these traits? So we have a logic that is next generated. If we remove the nucleus from the cell, will it not divide and grow? So that is a logic that needs to be tested. Okay. So based on the previous observations, to answer the questions, we created a logic, and for which you call a hypothesis. The nucleus contains a hereditary information. So that is a hypothesis, which can be proven or disproven. So then null hypothesis, it is something like removal of the nucleus from cell will not affect the development. So that is a null hypothesis. Now, if the null hypothesis is there, you just require to design an experiment to kill the nucleus. So if you kill the nucleus and it doesn't affect the cell development, then null hypothesis is actually supported. So the result is that cells do not develop. So you reject the null hypothesis, which means our hypothesis, that is the nucleus contains a hereditary element, can be supported. So this is how the process of science works. And sometimes we require ad hoc hypothesis. In science and philosophy, an ad hoc hypothesis is a hypothesis added to a theory in order to save it from being falsified. So there is every possibility that, or the basic feature of the hypothesis is that it is subject to be rejected. It is subject to disproval and rejection, subsequent rejection. So in science, usually the hypotheses were not entirely rejected on first observation of a of some negative result. So for which you propose an ad hoc hypothesis or some additional supplements, or some you will set some restrictive conditions so that it is not easily being falsified. Often ad hoc hypothesizing is employed to compensate for anomalies not anticipated in theory in its unmodified form. So if there is a theory and if there is some anomalies in the theory, to compensate that one, okay, it is not applicable in that condition. So you can keep a rider there, so that okay, this is the hypothesis, this is the law, or this is a theory, and usually it will happen, or this should happen, and not in that condition, or you will set some exceptions there, so that the ad hoc hypothesis will address that exception. The hypothesis is actually it was falsified because of some exceptional cases, and if you can reject the exceptional cases by adding an ad hoc hypothesis, then your hypothesis is saved from being falsified. So such type of hypotheses were known as ad hoc hypothesis. Scientists are often skeptical of theories that rely on frequent unsupported adjustment to sustain them. So usually theories actually they are always put on test, and there is a possibility for rejection for theories also, because if further evidences were gathered, certainly then they will be challenged and it will be rejected. This is because if a theorist so choose, there is no limit to the number of ad hoc hypotheses that can be that could be added. So if you have a theory and somebody else come up with an evidence that disprove your theory, then you will add something, some other rider, or you will add an ad hoc hypothesis that this is under these circumstances this is not applicable. You place another argument to support your theory. So such arguments were actually ad hoc hypothesis. Thus, the theory becomes more and more complex and never being falsified. Whatever proofs were raised against that theory, you will support further and further your theory by additional points, additional hypotheses. This is often at the cost of the theory's predictive power because you are adding more and more exceptions. So your theory's actual predictive power will be diminished. So at a stage where further ad hoc hypotheses were um, uh, not possible, then only your theory will be rejected. So until then, the theories can be supported with ad hoc hypothesis. Ad hoc hypotheses are often characteristic of pseudoscientific subjects because they always will try to prevent falsification. So this is an image taken from Wikipedia, and uh, there is a character like a leprechaunus, that is a dwarf figure, a mythical figure, and this is only a character. It's not, and in some of the epics or something. And if someone wants to believe in this leprechauns, they can avoid ever being proven wrong by an ad hoc hypothesis. Example, by adding they are invisible, and their motives are complex. So if you add say Kuttichadan or something, any other character or any other demon, you can hypothesize their existence. And whenever you are trying to prove something that okay, you can add another writer, though they are invisible. So okay, then you cannot prove it. And such type of additional points that is added to a hypothesis is known as a ad hoc hypothesis. An ad hoc hypothesis is not necessarily incorrect. In some cases, a minor change to save the theory or to the theory was that all was necessary to save the theory. So most of the cases it may be acceptable, but with some exceptions. But this can also be, as I mentioned, this can also be used for supporting pseudoscience. Some gaps in knowledge and even some observations that contradict a theory must be temporarily tolerated while research continues. So such gaps in the knowledge and such contradictions in the theory must be temporarily tolerated for some time for further testing and verification. That's always required because a simple evidence cannot or that should not be the reason for preventing further testing and research, and of course there should be a provision for further research and gathering further evidence in support of the theory. So these ad hoc hypotheses where usually it is required for tolerating minor errors in the theories. It is generally accepted, but it can also result in supporting pseudoscience also. And to temper these ad hoc hypotheses in science, common practice includes falsificationism. Falsificationism actually it means scientists become more likely to reject a theory as it becomes increasingly burdened by ignored or contradicting evidences and ad hoc hypotheses. So if there is a large burden of ad hoc hypotheses and other contradicting evidences gathered, then normally the theory is subject to be rejected and it needs to be falsified. So falsificationism demands such type of increasing evidence and also increasing burden of ad hoc hypotheses which were that were trying to save the actual theory. Now when we, this is a simple statement actually, when we talk about some hypothesis, the God actually the God is assumed to be omnipresent, omnipotent, and omnipotent means he can perform any task, anything. But if you ask a question like this, some of the atheists are actually asking this question: can God create an immovable stone? So this is a contradictory statement. If one part is true, if A is true, then B cannot be true, because God cannot create a stone or an immovable stone. So the same sentence is actually contradictory about both parts. If you create, then it is not immovable, and that part actually contradicts the statement like omnipotent, or he can perform any task. So that type of statements actually can be made also for in some hypothesis, and you can see that this type of this is not a subject of verification, as I mentioned. It's not a scientific question, because it is not possible to prove or disprove based on scientific observation, and even the existence of God is not it cannot be hypothesized, because it is not a scientific hypothesis. A scientific hypothesis needs a clear experimental or empirical evaluation methods, and that is not possible here. So there are such questions, such where there in which the question itself is, or the hypothesis itself is actually contradictory. The two parts will be contradictory. So if A is true, B cannot be true. Okay. Then the auxiliary hypotheses are sometimes called assumptions. Previously I mentioned the assumptions also, because we are assuming something. Some loopholes in the original theory or hypothesis were blocked or closed by such assumptions. The assumptions of a particular test are all the hypotheses that are assumed to be accurate in order for the test to work as planned. So you will assume that x is constant, then y will perform in a particular manner. So in that way you can assume something. Assumption is already explained in the previous slide. However, it is important to recognize that these assumptions are really hypotheses in disguise. The ideas which themselves could turn out to be too accurate or inaccurate. So actually these assumptions are also ad hoc hypotheses. All tests involve auxiliary hypothesis. Sorry. So sorry, ad hoc, auxiliary hypothesis. Auxiliary hypothesis, this is auxiliary hypothesis, not ad hoc. Okay, auxiliary hypothesis were assumptions. Assumptions separately discussed earlier. So auxiliary hypothesis were usually assumptions which place some restrictive conditions to the test, and all tests involve such a auxiliary hypothesis because we want to set some parameters. Your experiment is designed under some restrictive conditions. So all the restrictions applied to the experimental conditions were actually assumptions, and they are part of the auxiliary hypothesis. Here you can see that an example. There is a hypothesis or theory. The theory or hypothesis is that the rock is 3.8 billion years old. So we have an ancient rock, and we assume that this is 3.8 billion years old. So to test the hypothesis, we require some experimental portions like carbon dating, etc. And our expected result based on the science is that it is expected to have about 79 lead molecules and 206 atoms for every 100 uranium, and this is the total statistics which is given. Okay, so this is the composition of the rock that we are expected in carbon dating. So to prove that one, you can test that actually this is the expected scientific expectation, and by testing you can also prove that one using carbon dating, etc. So now you see that these both are same, so it supports the hypothesis. But when we are designing this hypothesis, we have to additionally add some auxiliary hypothesis. For example, auxiliary hypotheses were additionally applied in these hypotheses, like the half-life of the uranium is uranium-238 is 4.5 billion years. If it is a different one, then certainly this assumption will be different. So to reach this scientific calculation, you need to assume that the half-life of the uranium-238 is 4.5 billion years. If it is wrong, this result is wrong. The half-life has been constant throughout the time all through these 3.8 billion years duration, the half-life of the uranium should not have changed. Neither uranium nor lead has leached out of the rock since it is formed. All the molecules should be stayed in that vicinity, so that when you are analyzing, it should be there. And if it is leached out, then the concentration will be different. So our assumption is that the entire atoms created and converted, all atoms were there in the rock itself. And the sample rock has not been contaminated by external uranium or lead. So that possibility also should be blocked. And the equipment that we have that used should have an accuracy, optimal accuracy for detecting this one. So these all additional parameters needs to be applied on these contexts to reach this result. Otherwise, if any of these conditions fails, then the result will be different. So such type of hypotheses were known as a auxiliary hypothesis, which support or which place some restrictive conditions on the experimental design. If H, that is a test hypothesis, and H is a test hypothesis, and A, that is auxiliary hypothesis, are true, then I, that is a test implication of result, is true. So that's an a condition. You can something apply like this. An example also is given. If a childbed fever is caused by infectious matter H, so the hypothesis is a child fever is caused by infectious matter or infectious agent. So that is the hypothesis. And chlorinated lime destroys the infectious matter. So second statement, auxiliary hypothesis. Chlorinated lime destroys this infection or infectious agent. Then if persons attending these patients wash their hands in chlorinated lime is C. Wash the hands with chlorinated lime is the actual act, that is C. Then death from childbed fever will be reduced. So a complex statement or a hypothesis design, something like that. Okay. So we have a first hypothesis, that is the childbed fever is caused by infectious matter as a hypothesis. Then second one, it cannot be true if you are that it is destroyed by the infectious agent. So otherwise if you are testing the hypothesis with the nurses wash their hands with chlorinated lime and going to test the hypothesis, then it will fail, because the auxiliary hypothesis actually protects the hypothesis from being falsified. Okay, the lime destroys the infectious matter, so that's the auxiliary hypothesis that actually protects the test hypothesis. And if you are designing such restrictive conditions, if the chlorinated lime destroys the infectious matter, then the childbed fever will be reduced. So we have a complex condition. And in that case, you can reasoning something like this. In case 1, where it is true, H is true, that is if it is caused by an infectious matter and that matter is destroyed by chlorinated lime, if both are true, then I, the outcome or the result, is true. That is, the child is saved from infection if the handlers were washing their hands with chlorinated lime. So that is true. Okay. And in another case, it may be false. If the original hypothesis is false, then the result will be something like this. Either if I is false means the child is not saved at all. Or you can say that say H and A are true, and therefore if it is false, the result is false, or if you don't find a direct correlation with that result, therefore in the case of false, either H or A or possibly both are false, because one possibility is that H is not an infectious agent, or A is not protecting or A is not killing the infectious agent, or the chlorinated lime treatment is not killing the infectious agent. Both may be the result. So if the theory is actually it is false, then sorry, the hypothesis is false, our error may be at any stage. For example, the original hypothesis may be false, or the auxiliary hypothesis may be false, or both can be false. So this is how the auxiliary hypothesis actually protects the original hypothesis, and this is the best example. You can see that in this case, the original hypothesis, that is H, or the presence of the infectious agent, is supported with the second statement, because without the second statement, if somebody washes their hand with chlorinated lime and say that child is saved from infection, then the result is because of it is not because of H is not an infectious matter, but because H is killed by the chlorinated lime solution. So that condition is actually implied only when you are using the second auxiliary hypothesis, that is A. So then there are scientific observations. Scientific observations means when conducting scientific experiments, we need observations. Observations are made through our senses. Observations use the senses to gather information from the natural world. So that's how the experimental outcomes were recorded. Scientists will observe nature using our five senses: sight, sound, smell, taste, touch. All these are the five senses that is used for observing and recording the results. Observations are how scientific data gets collected in experiments, and observations can also lead to developing new experiments. So based on the observation, you can redesign the experiment, and that results in development of new experiments for validation of the hypothesis. Now, if the thing you are observing can be measured or counted, then you are making a quantitative observation. For example, if you said there are 5 frogs here, it would be a quantitative observation because you can give it a numerical value. So if you can count the results and give it a numerical value, then that is a quantitative observation. And if the thing you are observing can be really be measured, color, taste, etc., then it is a qualitative observation. Okay. So if you said that the young man here on the left is very small, that would be a qualitative observation. Okay, or this is tall and this is small or a dwarf. That type of observations were a qualitative observation which cannot be numerically explained.